Hello and welcome. I'm Dr. Mohan and I've been facilitating your physiology lectures for the renal component of MDSC 1102 for this year. You can find me in the physiology unit and my email address is at the bottom of this slide in case you have any questions as you go through the lecture outline. As mentioned previously in class, I'm sticking quite closely to your essential textbook simply called Physiology by Linda Costanzo because of her great diagrams and simple explanations, but I'll dip from time to time for more detail into the Bernoulli. The course objective for this physiology lecture can be found in the MDSC 1102 course outline, which I uploaded to My Learning at the beginning of the course. As with other lectures, I've subdivided today's topic into 3 subtopics. That is, a brief introduction, followed by internal potassium balance, which is the regulation of potassium ions across cell membranes, and finally, external potassium balance, which is the regulation of potassium excretion by the kidneys to match dietary intake. As you know, potassium ion is one of the most abundant cations in the body. So what springs to mind when you think of the function of potassium ion in the body? If you said it is required for the normal functioning of nerve and muscle cells, you would be right. Recall that even a slight change in the ratio of ECF potassium ion concentration to ICF potassium ion concentration can have a profound effect on nerve and muscle cells because this affects the potassium ion concentration gradient across excitable cell membranes, which in turn directly affects the resting membrane potential of these cells. Potassium ions are also necessary for several metabolic functions, as shown on this slide. Did you remember that most of potassium ion in the body is inside cells? Only 2% of total body potassium is extracellular, and the concentration is closely regulated at about 4 milliequivalents per liter. Movement of potassium ions out of cells can increase the concentration of potassium ion in the blood. This is a condition called hyperkalemia. Conversely, movement of potassium ions into cells can reduce the potassium ion concentration in the blood, and this is called hypokalemia. And don't forget about sodium-potassium ATPase, which maintains the concentration difference of potassium across the cell membranes. On the left of this picture, you can see the effect of normal concentration of plasma potassium ion on the resting membrane potential of a skeletal muscle cell. In the middle and on the right, the effect of hypo and hyperkalemia on the resting membrane potential of the same cell are shown. Since the diet usually contains adequate amounts of potassium ion, hypokalemia is usually due to losses of potassium ion from the GI tract or by the kidneys. Persistent vomiting or diarrhea, or the use of loop or thiazide diuretics are frequent causes of hypokalemia. Low plasma potassium, as we see in the middle graph, causes hyperpolarization of the resting membrane potential of the skeletal muscle cell, and so this makes the cell less sensitive to depolarizing stimuli and therefore less excitable. If the hypokalemia is severe enough, it can lead to paralysis. On the other hand, hyperkalemia, which can be caused by advanced renal disease when the kidneys are unable to eliminate potassium ions from the body, causes the resting membrane potential to become less negative, as you see on the right side of the picture. You might think that the cell then becomes more excitable, But in fact, this inactivates the fast sodium channels responsible for the depolarizing phase of the action potential, thereby reducing the excitability of the cell. In severe hyperkalemia, the resting membrane potential may even rise above the threshold, making the cells unable to repolarize after conducting an action potential, and this can lead to paralysis. So either way, you can see that alterations of potassium ion concentration outside of the normal range isn't good news. This picture shows the effects of hypo and hyperkalemia on the ECG. Here's the normal ECG in the middle with normal range of plasma potassium. As the plasma potassium falls, there is a low T wave, and as it falls further, this is accompanied by the appearance of a U wave. Then, with a further fall in plasma potassium, the ST segment is also lowered. In hyperkalemia, there is a characteristic tall peaked T wave. Then, as there is a further rise of plasma potassium, this is accompanied by a prolonged PR interval, and eventually, at a potassium concentration of about 10 milliequivalents per liter, the P wave disappears, the ECG appears as a sine wave, and the ventricles fibrillate. Let's explore how potassium ion concentration is kept fairly constant in the body. Basically, there are two sets of regulatory mechanisms. One set regulates the movement of potassium ions between the cells and the ECF, that is, they're responsible for internal potassium balance. And another set regulates potassium ion excretion by the kidneys to match dietary intake, that is, they are responsible for external potassium balance. I'll talk about those that maintain internal potassium balance next.